In the previous lesson, we talked about how we can use vapor pressure data to determine the activities of solvents and volatile solutes. Now, in this lesson, we're going to deal with non-volatile solutes. So we can't use vapor pressure data because these non-volatile solutes don't have appreciable vapor pressure that we can measure. However, this approach we're going to use here, we still use vapor pressure data because that would allow us to determine activities of the solvents. Once you know the activity of the solvent and how it changes versus composition, then you can just use the Gibbs Duhem equation to figure out the activity of your solute. So the Gibbs Duhem equation, if you recall, is x1, a small fraction of component 1, d mu 1 plus small fraction of component 2 times d mu 2 is equal to 0, where mu, we said, is a chemical potential. It's partial molar Gibbs energy. So mu 1 would be partial derivative of G with respect to N1 at constant temperature, pressure, and N2 constant. Okay? So what this is saying is the changes in the chemical potential are actually related. So that means the activities are also related. Okay, so mu1, if you recall, okay, chemical potential of component 1 would be whatever its ideal value would be. Okay, for example, if you're dealing with an ideal gas, it's going to be mu naught plus RT ln PA over P naught if P sub A is the partial pressure of gas A. Okay, that would be the ideal value. And then you add a correction term, RT ln gamma, where gamma would be your activity coefficient. So we said gamma times P sub A would be the activity, over P naught would be your activity. Okay? So similarly, you can say that chemical potential for component number 2 would be whatever its ideal chemical potential is, plus RT ln gamma 2. Okay? So given from the Gibbs Duhem equation, we can rewrite our Gibbs Duhem equation this way. We can solve for d mu 2. You can see that d mu 2, okay, x1 d mu 1 plus x2 d mu 2 equals 0. Okay, so we move this over to the right. That gives you mu 2 dn x2 d mu 2 is equal to negative x1 d mu 1. So d mu 2 would be negative x1 over, oops, sorry, this should be x2. Negative x1 over x2 d mu 1. Okay, what this means is that the chemical potential of component 1 goes up. Okay, if this is positive, then d mu 2 is going to be negative. So if d mu 1 is positive, d mu 2 is going to be negative. Chemical potential of component 1 goes up, the chemical potential of component 2 must go down. And the relationship is given by this equation, so it depends on the mole fractions of components 1 and 2. Right? So we substitute our expression for mu1 into here to get d mu 1, and our expression for mu 2, oops, got it switched. We substitute the expression for mu1 over here to get d mu 1, and the expression for mu 2 over here to get d mu 2. And what do we get? We have d mu 2 is, okay, constant temperature and pressure. This is just going to be a constant, so it's just going to be RT times D of ln gamma 2, because your gamma 2, your activity coefficient, is going to depend on what the concentration, what the composition of your mixture is, what mole fraction is. All right? And then the right-hand side of this equation is negative x1 over x2. D mu 1 would just be derivative of a constant plus derivative of RT ln gamma 1, and again, derivative of constant is just going to be 0, so you'll have RT times the differential of ln gamma 1 on the right-hand side. Okay, so all we have to do now, okay, first of all, you can cancel RT, so this ends up giving us d ln 2, okay, This is d ln 2, and x2 is just 1 minus x1, d ln gamma 1. All right, so the strategy then is this. If you know, okay, you can measure, you can actually determine gamma 1, okay, for the solvent. So we're going to call component 1 our solvent. If we know gamma 1 versus mole fraction of solvent, x1, then everything here on the right-hand side, you would know, okay? So what you'll need to do is to get ln of gamma 2, okay? Integrate both sides of the equation. So it would be integral of negative x1 over 1 minus x1 d ln gamma 1. If you integrate this, you integrate this from pure x1, so when x1 equals 0 to whatever x1 is. Okay, sorry. Wrong limit. It should be whatever the value of ln gamma 1 is when x1 equals 1, okay, when you have pure x1, okay, and so if you have pure x1, we expect gamma 1 to be equal to 1, so ln of gamma 1 would be equal to 0. So this thing down here, the lower limit, would just be 0, and here you'd have ln of gamma 1 at whatever mole fraction for whatever solution you're interested in, okay, at the x1 of the solution. Okay, and so what you can do, that will give you, if you integrate the left hand side, this would be ln of gamma 2 at with pure x1, pure solvent. Okay, and so this is going to be a very dilute solution, so ln gamma 2 again, gamma 2, you expect this to be equal to 1, okay, it's ideal. Remember we said gamma is 1 if you're dealing with an ideal solution, so ln gamma 2 here would be equal to 1, so this is 0, and here would be ln of gamma 2 for whatever the solution you have is. So this will give us ln of gamma 2, okay, would be equal to integral of negative x1 over 1 minus x1 d of ln gamma 1, okay, from 0 to ln gamma 1. Now, so let's illustrate that with data from your textbook. An example, problem 5.1 in Atkins, you have you're given the mole fractions, a series of solutions with a mole fraction of component A ranging from 0 to 1, okay, and in that problem you're given the mole fraction of A in the vapor, so x sub A is the mole fraction in the liquid, mole fraction y sub A is mole fraction in the vapor, and the total pressure of the vapor in equilibrium with the liquid is tabulated here for the P column. Okay, and this is in torr. And so from here you can see that when mole fraction of A is 1, the vapor pressure is 12.295. So P star A then we say is 12.295. Okay, that's the vapor pressure of pure A. When the mole fraction of A is 0, that means you have pure B. So P star B would be the vapor pressure at that point for that particular liquid, it's 36.066. So P star B right here is 36.066. So this is the data given from the problem. All right. Now, you might say this deals with volatile components. A and B are both volatile. Well, the Gibbs Duhem equation actually works whether or not you're dealing with a volatile or non-volatile solute. Okay, it's just it's the only way you can do activity coefficients if you're dealing for solutes if they're non-volatile. So we can still illustrate the Gibbs Duhem equation using this particular example. Okay, so how do we actually determine the activity coefficient for solute? Let's call B our solute. So this is our solute, okay, and this is our component 2, okay, and A would be our solvent, okay, and that's going to be our component 1. All right, so let's calculate from the vapor pressure of A, partial pressure of A above the mixture. You can actually calculate its activities, right? So here what we've done is from the data, remember this is our data, let me highlight the actual data. And that's your actual data. From the data, you can calculate the partial pressure of A in the vapor, and that is simply piece of A is just mole fraction of A in the vapor times the total pressure. So it's mole fraction times the total pressure. Okay. Get rid of that. Okay. So if you look at, for example, this one right here, okay, formula from that, that's just B7 here. That's column B, row 7. So that's the mole fraction of A in the vapor times the vapor pressure. That gives you the partial pressure of A in the vapor. So I just copied that down to the rest of the column. Okay. Similarly, you can calculate the partial pressure of B. That's just the difference between the total pressure. Okay. Total pressure right here. Oops. Total pressure minus the partial pressure of A. Okay. And you can calculate mole fraction of B in the liquid. This is just 1 minus the mole fraction of A in the liquid. So this X of B is the mole fraction of B in the liquid. How are we going to calculate gammas of A? You can use Raoult's law. Okay. Gammas of A, if you recall, the activity is just P sub A over P star A, right? And that's just equal to gamma times mole fraction of A. So that means gamma sub A, to make a distinction between gamma sub A and gamma sub B. Gamma sub A, the activity coefficient for A, would just be equal to partial pressure of A over PA star times mole fraction of A. In other words, this is what this one is the actual partial pressure of A, and this is what the partial pressure of A would have been if A was behaving ideally, not disobeying Raoult's law. P star A times X of A would be the partial pressure of A if it were to obey Raoult's law. So if these two are equal, then your gamma sub A is equal to 1. Okay? So let's see. What do we have here? You can see over here that gamma sub A is just equal to, I entered the formula here. Oops, pressed the wrong button. Okay, the formula here is just 1. Okay, because P star A over PA, so that really should be PA divided by P star A. Okay, so that's 1. And if I want to copy that down to the rest of the column, I make my B1, my reference to B1 absolute, so it won't change when it's copied down. Okay, so let me go ahead and copy that down. Drag this one, copies it down. Okay, so this one right here, gamma sub A, would be, oops, I think I did the wrong thing. Back up. Okay, this one right here, you'll notice this is, okay, this is D7, which is PA right here, okay? Partial pressure of A divided by mole fraction of A is A7 times P star A. So the partial pressure of A, the actual partial pressure, and then this is the Raoult's law prediction for the partial pressure if it were ideal. Okay, so that's how you determine your gamma sub A. Now, gamma sub B can be calculated, but this is assuming Raoult's law. Okay, it's just going to be equal to partial pressure of B divided by mole fraction of B times partial vapor pressure of pure B. So E7 right here is partial pressure of B. That's your numerator. Okay, so gamma sub B, recall. gamma sub B is just PB over PB star XB, same formula, okay? So that's gamma sub B. And that's this one right here. So you can actually calculate it. But we're going to try to calculate gamma sub B. We're going to illustrate how you could calculate gamma sub B if B were not volatile. Okay, using, actually you can, even if it's volatile, you can still calculate it using the Gibbs Duhem equation. So what we're going to do is we're going to calculate ln of gamma sub A. So this one right here is a natural log of gamma sub A. And this one over here is negative XA over XB. Right, so let's take a look at those formulas. This one is ln of, so that's ln of A, okay, gamma A, ln of G6. This is ln of G7. This is ln of G8, and so on. All right, and then negative X of A over X of B, okay. This is going to be, for the first one, it's going to be undefined. It's going to be negative infinity because X of B here is going to be 0. Right, so we're not going to calculate that. Negative X of A over X of B here, okay, would be, here's X of B, 0.08, X of A is 0.9105, okay, over X of B, which is 0.0895. So negative A7 over F7. This one is negative A8 X of A over X of B. So negative 0.8019 divided by 0.1981. And this one is that, and so on. Okay, so those are your negative values of negative X of A over X of B. So you're going to plot negative X of A over X of B versus ln of gamma A, and this is what we get. Okay? So notice that as you go to, look at what happens to your X of A, to your solution. Remember, okay, we're treating A as a solvent, so this solution is dilute right here, right? So at very dilute solutions, this ratio, negative X of A over X of B goes to negative infinity. Right, so I have very dilute solutions here. So if we had extra data here, you would, okay, if we had extra data here, you would see this go further down. Okay, so let's say you wanted to know for this one to this second data point right here, okay, what the ln gamma sub B for that is going to be. What's gamma sub B for that is going to be? What is the activity coefficient of component B for that particular solution? So what you do is you integrate, okay, remember you integrate negative XA over 1 minus XA, right, D of ln gamma A from, okay, 0 in this case, right, to whatever your ln gamma sub A is for that mixture, for that solution. So up to ln gamma sub A, from ln gamma sub A equals 0 up to the ln gamma sub A of your solution over here. So, and then, so this one, you need the area under this curve. That's going to be your integral. And that is going to be equal to ln of gamma sub B. Okay? So gamma sub B would just be equal to E to that area under the curve right there. Now you can see this goes to infinity, but ultimately, eventually, that's going to approach 0, okay, at some very dilute solution. So this is, you can have a finite area right there. All right, so one method that I find useful, and I haven't seen this in any textbooks, so this is something I just came up with, is what you can do is you can actually plot ln gamma instead versus x2. And so you can express ln gamma 1, which is gamma sub A, or solvent, and you can wrix it as ax cubed plus x2 cubed plus bx2 squared plus cx2 plus d. Okay, you can fit it to a polynomial. Okay, and so you can usually fit most data with a polynomial. And then what you do is you now have ln gamma 1 as a function of x2. So this integral over here, you can rewrite this. Okay, and what you do here is you can just say this is going to be now equal to negative x. I'm just going to put everything in terms of x2. So instead of x1, I'm going to write 1 minus x2. Okay, and the denominator would be x2. And instead of writing d ln gamma 1, I'm going to use the chain rule. So I'm going to say derivative of ln gamma 1 with respect to x2 dx2. So I've changed my integration limit. So this is now at x2 equals 0, and this is at x2, or whatever x2 of the solution is. And that's a much easier way to do it. This would be ln gamma at x2 of the solution. So it's gamma 2. Okay, the left-hand side, minus ln gamma at x2 equals 0. Okay, and now this lower limit can, if you actually know the value of ln gamma 2, okay, for some dilute solution, let's say at x2, sorry, let's say at x low, okay, a low concentration. If you know ln gamma 2, then you can put that here, and then instead of ln gamma 2 at x2 equals 0, you can put ln gamma 2 at x2 equals x low, and you won't have to worry about this quantity right here, this ratio of the mole fraction going to negative infinity. Okay, let me illustrate that. Okay, so here's the same data from Atkins, problem 5.1, Atkins 8th edition. So this is the data. All right. You're given the mole fraction of A in the liquid, its mole fraction in the vapor, and the total vapor pressure. All right. And so what I did here, we did this earlier. We calculated ln gamma, if you remember. Okay. And so ln gamma is plotted here versus mole fraction of B. Okay, so this graph right here, is a plot of ln gamma versus mole fraction of B. And I am going to start with I'm going to pretend I know that gamma sub P for mole fraction of 0.1981 is known to be 1.1879125. Okay, and so what I did here was I fitted ln of gamma sub A with respect to mole fraction of B to a polynomial, and that's very easy to do in Excel. All you have to do is, once you've graphed it, you just right-click, add a trend line, and then you do a polynomial trend line. You can do a third-order polynomial or second-order polynomial right there, and then I can format my trend line to display the equation on the chart and display the R-squared value so you can see how well it fits. To minimize round-off errors, it's best to format your data trend line label so that the numbers are shown with as many sig figs as possible. So I use 5 sig figs, scientific notation. Okay, and you can see that those are the coefficients. So this is ax cubed plus bx squared plus cx plus d. So I copy that to a MathCAD document. All right, so this is the how I would work this out on MathCAD. So here's my ln gamma sub A as a function of the mole fraction of B. So ax cubed plus bxb cubed plus cxb plus d, where these are the A, B, C, and D from my Excel regression polynomial fit. Okay, you should be able to do polynomial fitting on MathCAD as well. All right, so anyway, this is my ln gamma versus mole fraction of B, and if you were to plot that, So you can calculate gamma as a function of the mole fraction of B would be gamma for A, okay, as a function of the mole fraction of B would be e to this ln of gamma as a function of mole fraction of B. And if you were to plot that, this is what you get, okay, this graph right here. And this is the same graph we had in Excel. I just transferred the data. So I have gamma here, gamma sub A from the data. These are represented here by the blue circles. And then the polynomial fit of ln gamma versus mole fraction of B. So this is mole fraction of B right here on this axis. Is shown by this red curve. So I know I can verify that I have my polynomial does fit my experimental data. Once I've done that, what you do next is you say ln gamma sub B, this is now ln gamma 2, okay? We're going to make that a function of x, x2, or x sub B. I'm just going to make that generic, so this is just a generic variable. X would be the integral from, okay, a concentration of B, a solution where I know mole fraction of B is 0.1981 and gamma sub B is 1.1879. So when mole fraction x sub B is equal to 1.1981 according to my data, okay, so I'm pretending here that I know that, okay. So if you go back to your Excel spreadsheet, you can see right here when mole fraction of B is 0.1981, right here, gamma sub B is 1.1879125. All right. So this is really, okay, ln of that minus ln of this would be equal to this thing right here. So I just moved this one over to the right side. Okay. So what do we have here? We have ln of gamma sub B would be equal to ln of 1.1879. This is gamma sub B at xb equals 0.1981. Okay, that's my lower limit. So I'm going to integrate that from my lower limit to whatever mole fraction I'm interested in. Okay, and so what do you have here? This is negative of 1 minus xb over xb. So that's negative xa over xb. Okay, that's that one. And what do you have over here? What is this? That's just the derivative of ln gamma sub A with respect to xb. Okay, remember we said we fitted ln gamma sub A to be ax cubed plus bx squared x sub b plus bx sub b squared plus cx sub b plus d. So that's just the derivative. That's 3ax sub b squared plus 2b x sub b plus c. Okay, that's how you take your derivative. And then integrate over x sub b from x sub b equals 0.1981, the lowest concentration that I'm going to be basing it on, for which I know the activity coefficient, up to whatever the mole fraction is of B in the solution I'm interested in. Okay, so that's your ln of gamma x sub b. So gamma x sub b would just be, gamma as a function of x sub b would just be the inverse log of this expression right here, so the inverse log of that. So e to the ln gamma b, gamma sub b as a function of x sub b. If I were to plot that, this is what you'll find. Okay, here's the blue curve right here. This is the calculated gamma sub b as a function of x sub b. All right, and your green dots here, your green circles, would be your experimental data. Actually, that's the based on Raoult's law. Okay, so this is the gamma sub b based on the vapor pressure data. Okay, this is not something you would have available to you if you were dealing with you're dealing with a non-volatile solute. But in this case, that's available to you, so you can verify that the Gibbs Duhem equation does work. Okay, and of course this one right here, the red curve is just gamma sub A, gamma for the solvent. All right. Okay, so moving on. Let's talk about electrolytes now. As you recall from freshman chemistry, ionic compounds are typically non-volatile, so we could use what we just learned about using the Gibbs Duhem equation to determine the activities of non-volatile solids for electrolytes. There's an additional problem you have to deal with electrolytes in that they split into ions when you put them in solution. Okay, so you cannot really just measure the chemical potential of a particular ion because they always have to, electron neutrality condition requires that you cannot just put magnesium ion in solution. It has to come with a negative ion. So what we need to do is then define a chemical potential for an electrolyte itself, a compound that's in aqueous solution. Okay, an ionic compound in aqueous solution, we define its chemical potential as the chemical potential of the cation plus the chemical potential of the anion, each one multiplied by a stoichiometric factor that depends on what the formula of the compound is. So magnesium chloride gives you magnesium ions and 2 chloride ions in solution. So the chemical potential of magnesium chloride would be whatever the chemical potential of magnesium ion is, which we cannot measure, okay, plus 2 times the chemical potential of chloride, which we also can't measure, but we can define a chemical potential for the sum of those two. Okay, so chemical potential for magnesium ion, then we can say is equal to its chemical potential in its standard state plus RT times natural log of the activity of magnesium ion plus 2 times, and then to get the chemical potential for the electrolyte, you add to that the 2 times the chemical potential of chloride. So chemical potential of chloride is its standard chemical potential plus RT times natural log of the activity of the chloride ion. Okay, and so this is our expression right here for the chemical potential of magnesium chloride. Now, let's combine these standard values for the ions into one. We call that the standard chemical potential of magnesium chloride. Okay, aqueous solution plus, and we'll combine these two expressions on the right here. RT ln A of magnesium plus 2 RT ln A of chloride. So this is like 2 ln x. This is like ln of x plus 2 ln of y. You can combine these two by saying you have ln of x plus ln of y squared, and you can combine those two. You can say that's ln of x times y squared. All right, so here you have, okay, you factor out the RT, all right, and so you have ln of activity of magnesium times the activity of chloride, and the 2 we move it inside, so that's chloride squared. All right. Once you have that, all right, you can then say that the activity of magnesium would just be equal to the molality of magnesium ion over m naught, where m naught is 1 molal because activity has to be a unitless quantity, and the activity of chloride would be the molality of chloride divided by m naught. All right, so you have activity of magnesium right here, and you have activity of chloride, all right, squared. All right. Now, this is the expression you get if you have an ideal solution, right? When the activity is just equal to m over m naught, but we do know that if you have non-ideals in general, when we have real solutions, you have to multiply this by the activity coefficient of magnesium, and you'll have to multiply this by the activity of chloride. So here you have that extra term RT ln gamma of magnesium times gamma of chloride squared. So this is the correction for non-ideal behavior. Once you've done that, let's do some further manipulation here. You can see this is mu naught of MgCl2 plus RtLn. Okay, what do we know about molality of magnesium? It's the same thing as the molality of your magnesium chloride. All right, so we're just going to represent that by M. All right, so this is just M. What's the molality of chloride? Molality of chloride is 2 times the molality of magnesium chloride. So molality of chloride right here is 2M. So this is 2M over M naught, and that one is M over M naught. But then you have to square 2M over M naught, so you have a factor of 4 here. Okay, and then so if you do that, you have so you have M over M naught times 2M over M naught. That gives you 4M over M naught squared. All right, I mean cube. So this is power 1, and that's squared, so that's a power 3. Okay, so this term is cubed right here. And so 4M over M naught cubed plus RtLn gamma magnesium, activity coefficient of magnesium times activity coefficient of chloride squared. All right, since we cannot really, like I said, measure individual activities for ions, so we cannot get individual activity coefficient for ions, we can define what's known as the mean ionic activity coefficient. So gamma with the plus minus label next to it is this expression right here. Gamma, in this particular case, gamma of magnesium times gamma of chloride raised to the power 2. Okay, so this is like 3 gammas being multiplied, right? So you raise it to the power 1/3. Get the cube root of that to get the mean ionic activity coefficient. All right, so that's your mean ionic activity coefficient. All right, so that whole expression is gamma plus minus, and so if you did that, you end up, you can simplify your expression. You can now say mu naught equals mu equals mu naught of magnesium chloride plus RT ln of, okay, this is gamma plus minus M over M naught, and remember what happens to our M over M naught, we raise it to the power 3. Okay, this 3 right here is represented by this letter right here. Nu is the total number of particles you get from your electrolyte. So magnesium chloride, okay, would give you 1 magnesium and 2 chlorides, so 1 plus 2 is 3. Okay, so and then nu plus minus over here, so it's gamma, and there's a nu plus minus. Nu plus minus, that's the 4 that we got. Okay, so nu plus minus is saying you get 1 cation and 2 anions. You have to raise that to the power 2. That gives you 4. Okay, and you take the cube root of that, 1 over, raise that to the power 1 over nu. So 4 raised to the power 1/3. Okay, so that simplifies the expression we have for chemical potential of an electrolyte. This is right here. Mu naught magnesium chloride plus RT ln nu plus minus gamma plus minus M over M naught raised to the power nu. Right. Let's illustrate that with another problem, with another example. Let's look at what would be the expression for the mean ionic activity coefficient for sodium phosphate. Sodium phosphate is Na3PO4. So it's going to give you 3 sodium ions and a phosphate ion in water. So nu is equal to 4. Okay, there's 3 here and there's 1 there. So that means gamma plus minus is equal to gamma sodium times gamma phosphate raised to the power, gamma sodium is raised to the power 3. And then this whole expression right here is raised to the power 1/4. Okay, what would be our new plus minus for this one? Our new plus minus would be 3 cations raised to the power 3, 1 anion raised to the power 1, the whole thing raised to the power 1/4. So that gives us 9 raised to the power 1/4. Okay, so that's our new plus minus. So how would we write our mu for this one? Mu is equal to mu naught of sodium phosphate, okay, plus RT ln, okay, new plus minus, so 9 raised to the power 1/4, gamma plus minus, okay, times m over m naught, okay, the whole thing raised to the power 4. Alright, so let's talk a little bit more about electrolytes, ionic solutes in water. The Coulombic attractions between ions in water can lead to a significant deviation from ideal behavior, even in very dilute solutions. And so if you have ions in solution, obviously you're going to have positive and negative ions. So each ion in solution would actually be surrounded by counter ions of opposite charge, which would be attracted to it. So the net effect of all of these interactions is that you have a significantly lower chemical potential for ions in solution compared to the ideal solute particles. So activity coefficient for ionic solutes we expect to be significantly less than 1. Okay. At theoretic, the activity coefficients for ions can be calculated theoretically using the Debye Huckel theory, and the Debye Huckel's limiting law predicts will allow us to calculate coefficients for ionic solids in very dilute solutions up to concentrations of 0.01 molar for a 1-to-1 electrolyte. A 1-to-1 electrolyte is one where the cation has a charge of +1 and the anion has a charge of -1. Okay, when charges are much higher, you get much stronger attractive forces between the ions. Stronger interactions between the ions, like a +2 and a -2, a 2-to-2 electrolyte, then you can only get accurate predictions up to about 0.002 molar. All right. And the equation, okay, we're not going to go through the derivation of this. The equation from the Debye Huckel theory is given by this: log of gamma plus minus. Gamma plus minus is the mean ionic activity coefficient, can be shown to be -0.501 times Z plus, that's the charge of the cation, okay, and absolute value of Z minus, so that would be the charge of the negative ion, of the anion. All right. And I sub m here is called the ionic strength. Okay, m naught is 1 molar. And you calculate the ionic strength by just multiplying the molality for each ion that's present in the solution by the square of its charge, add them all up, and then divide by 2. All right, so this is the Debye Huckel limiting law. Let's illustrate that. With this one right here. So let's say you have a 0.01 molar solution of KCl. Now, 0.01 molar is approximately equal to 0.01 molar, because when you're dealing with dilute solutions, molarity and molality are essentially the same. They're aqueous solutions. All right, so let's compare the activity coefficient for KCl. 0.01 molar. All right, so what we're going to do is calculate first the ionic strength. So for the 0.01, let's just say 0.01 molar instead, okay? So we calculate the ionic strength would be 1/2 times molality of K plus is 0.01. The charge of potassium is +1 squared, plus molality of chloride is 0.01, and the charge of chloride is -1, so you square that, and that gives you the ionic strength of the solution. So the ionic strength is just equal to 1/2, okay, times 0.01 times 1 plus 0.01 times 1. So that's just going to be 0.01 molar. Okay, so I over m naught would be equal to 0.01. So that's your ionic strength. You plug that into here, 0.01, and your ionic strength is 0.01 over here. Z plus, the charge of potassium ion is +1. The charge of the chloride ion is -1, and you're just going to take the absolute value for that one. All right. So if you did that, what do you get? Let's see. Okay, what's our equation? -0.501, so log of gamma plus minus. Make this smaller. Log gamma equals -0.501 times Z plus Z, I'm going to say Z cation times absolute value of Z, Z anion, I'm just going to use absolute value there when I enter it later, times ionic strength raised to the power 1/2, so square root of ionic strength, over 1 plus the square root of the ionic strength. Alright, so I have to define Z cation is +1. Alright, Z anion is 1. I'm just using the absolute value. And my ionic strength is 0.01. And that gives me log of gamma. Oops. Log of gamma is equal to -0.046. So gamma equals 10 raised to the power log of gamma. So gamma equals 0.9. Okay, so the activity coefficient, even for 0.01 molar, is very, it's already significantly less than 1. It's 0.9. The literature value is 0.902. Now, what would happen if you're using a 0.1 molar? Well, if it is 0.1 molar, what would be your ionic strength this time? If this was 0.1, and that's 0.1, then this is going to be 0.1, that's 0.1, your ionic strength is going to be 0.1. So let's change our ionic strength to 0.1. If I change my ionic strength to 0.1, you can see my gamma is going to be 0.758. And the literature value is 0.770. So you can see it's significantly in error now compared to a 0.01. All right. Let's try calcium chloride at 0.001 and 0.01 molar. So let's calculate the ionic strength for calcium chloride. So 0.001 molar, let's just say molality, would be, ionic strength would be 1/2 times, molality of calcium is 0.001. Okay, so this is your calcium. Charge of calcium is +2. Alright, you square that. Plus, concentration of chloride is 0.002. This is your chloride. Okay, there's 2 chloride ions in 1 calcium chloride. So it's going to be 0.002, and then the charge of a chloride ion is -1. You square that. So your ionic strength is 1/2 of 0.001 times 4 plus 0.002. And so that should give us 1/2 of 0.004 plus 0.002. That's 0.006 divided by 2. That's 0.003. So that is your ionic strength. So you plug that into here, 0.003, 0.003, and your calcium has a charge of +2, chloride has a charge of -1, absolute value of that is 1. So let's go back to our MathCAD document. So Z-cat ion this time is 2, Zn ion is 1, ionic strength is 0.003, and you can see that our gamma activity coefficient is 0.887. Not bad, okay? 0.001 at low concentration, but that's a very low concentration. Let's try 0.01 this time. Remember, our 0.01 for KCl was 0.9, so it's pretty close to the literature value. Let's look at 0.01 for calcium chloride. What would that be? So this is going to be, if this is 0.01 and that's 0.02, this is going to be 0.01, 0.02. This is going to be 0.04, and this is going to be 0.02, and that will be 0.03. So if we do 0.03 instead for your ionic strength, you get, let's change our ionic strength to 0.03, and you can see that it's 0.711, okay? So 0.711, compare that with the literature value of 0.732, and this is 0.887. So you can see there's now a significant error, even at a fairly dilute 0.01 molar solution. Okay. Now, you can improve the accuracy of your theoretically calculated activity coefficient by making an empirical adjustment. Empirical simply means it's based on empirical data of the Debye Huckel equation. And if you use what's called the Davies equation, you'll be in error by about 1.5% at 0.1 molar or 0.1 molar, and about 5 to 10% when you get up to 0.5 molar in terms of your ionic strength. Okay, so the Davies correction is really just this: you subtract 0.3 times ionic strength from this expression right here. There are more complex theories that you can use to theoretically calculate activity coefficients for ions, and this is a good reference. Pitzer, Accounts of Chemical Research, Volume 10, page 317, 1977. Finally, let's talk about the effect of pressure on activities. Basically, what we are assuming that in all our previous discussions that the pressure was at P naught, right? 1 bar pressure. What if the pressure is not at 1 bar pressure? Then there will be an additional term for the additional change in the chemical potential given by V bar delta P. Why is that? Remember, dG is equal to minus S dt plus V dP. And so dG bar at constant temperature is just going to be V bar dP, okay? And so you need the partial molar volume right here, and that should be pretty close to the molar volume of the pure component. So this extra term in your chemical potential, let's call that RT natural log times an additional factor C that we have to multiply our activity with, okay? So you can see that additional factor C will just be equal to E to the V bar delta P. Okay, so delta P is P minus P naught over RT. Okay, let me clarify that. divide both sides by RT, right? T. So we can solve for C. C will just be, this extra factor will just be equal to e to the v bar p minus p naught, that's your delta p, divided by RT. So this is extra factor that you have to put in to multiply the activity at P naught. Right, so by what percent does the activity of water change if it's an external pressure of 10 bar instead of 1 bar at 298 Kelvin? Just assume that the molar volume of water, partial molar volume, is 0.018 liters per mole, 18 mils per mole. Then you say E to the 0.018 liters per mole. Delta P would be 10 bar minus 1 bar, okay, divided by R. Okay, so this is liter bar, so we use 0.08314 liter bar per mole Kelvin times temperature of 298 Kelvin. Right. So Kelvin cancels out, mole bar cancels out, mole cancels out, liter cancels out, so that quantity is unitless. So let me bring up MathCam to quickly calculate that. So you have E raised to the power 0.018 times 10 minus 1 divided by R is 0.08314 times temperature is 298. That's 1.007. Okay? So you're multiplying it by 1.007, you're looking at an increase of 0.7%, going to 10 bar. So pressure will hardly affect the activity of solids and liquids in mixtures. So to summarize, as far as activities are concerned, if you have an ideal gas, it's P over P naught. For real gas, then you just multiply the pressure by the fugacity activity coefficient. So that activity coefficient times P is called fugacity. If you have ideal liquids, your activity is just the mole fraction, okay? And you can determine that from the vapor pressure. So if you have a liquid A as part of a mixture, then its activity is PA over PA star. Okay, and that's going to be equal to XA if it's ideal. You multiply it by gamma, and so gamma times XA is the activity. All right, so PA over PA star is the activity, so that's equal to gamma XA. So it's going to be equal to XA, the mole fraction of A, if your liquid is ideal. If you're dealing with volatile solids, it depends on what convention you're using. You can use the molality convention. So you can, whatever the molality is, divided by 1 molal. That would be your activity. Ideal dilute, you multiply by gamma if it's not ideal. And the way you actually measure it is you look at the partial pressure of your solute in the vapor divided by the Henry's law constant. Okay, same thing. If you use mole fraction, that would be your activity. If it's ideal dilute, and you can determine that by measuring the partial pressure of the solute in the vapor by the Henry's law constant, and if it's not ideal, you'll have to multiply that by the activity coefficient. If you're dealing with non-volatile solids, use the Gibbs Duhem equation. So you use the activity of the solvent to figure out the activity of the non-volatile solid. And if you're dealing with electrolytes in particular, you may use the Debye Huckel Limiting Law or the Davis equation if you want to go up to about 0.5 mole of solutions. Okay. The effect of external pressure would be simply to multiply whatever activity you have by E to the V bar times P minus P naught over R2, where V bar is your partial mole.